Hello, everyone, and welcome to another wonderful, great day of PChem. So today we're going to be essentially branching into a new field of mathematics, which we're going to be able to use to really explain most of the rest of what we do this semester. So one of the things that we can start using all those wave functions that we've taken a lot of time building up is apply them to something called an operator form of mathematics. So the general idea of the operator form of mathematics is you apply some operator, which is usually some sort of mathematical operation. So multiplication, division, uh, rarely addition or subtraction, but very often differentiation. So what we can do is apply this type of mathematical operator to some sort of mathematical function. For us, this is typically going to be our wave function. So when you apply this operator to our wave function, you're going to get some new mathematical function back out. Where again, our mathematical operator is just any mathematical expression that can act on a function. So you think of a thing you can do to a mathematical expression, that's probably an operator. Now, one of the things that makes quantum mechanics so nice is that it actually exists in a special form of operator mechanics. And that's known as eigenfunction systems. So what happens if you have an eigenfunction is when you apply my operator to my mathematical function, what it does is it gives that same function back. And it gives it back differing only by a constant, so some numerical value. So let's say I have a function that has a dependence on x, so something with a dependence on position. Well, I'm going to get that same wave function back, and the only difference is going to be the mathematical number involved. So this should start looking familiar as we brought this up before, but we can often shorthand this notation as I'm going to indicate a general operator with an omega with a hat. So that's this little bracket above hand is called a hat. So this is omega hat. It's the operator that gives me the eigenvalue of omega. So if I want to know the energy, I apply the energy operator. I want to know position, I apply a position operator. I want to know I want to know energy, momentum, position, anything you can imagine. You just apply the relevant operator. You apply that to your wave function, you should get your wave function back, and then the actual value you're interested in. And this is really where wave functions start to shine. And it's the reason I called them an oracle. You ask a question, that's your operator, you get your eigenvalue back. Question, answer. That's more or less operator mechanics. Now, this should look vaguely familiar as we've already introduced one of the most popular eigenfunction systems in existence, and that's the Schrodinger equation. So the Schrodinger equation, the Hamiltonian, is going to be my operator, and it's going to be given by a fairly general equation. So the equation includes a first part, which represents the kinetic energy, which just involves our h bar squared over twice the mass, and then the second derivative with regard to position. Then we have a second part of our operator, which is going to be the potential operator. And this is going to, this potential portion of the operator is going to be dependent upon exactly what system I'm studying. So if I'm looking at an electron, I have to look at what's the potential field, or more precisely, how much the electron wants to exist in one position compared to another one. And we're going to be spending most of the rest several weeks really diving into this Hamiltonian operator because there's a lot to unpack here. And so I can apply my Hamiltonian operator to my wave function, and I should get my energy back and my wave function. This is exactly what's been essentially dominating what wave functions we can choose, is because we need to have a wave function that gives itself back. This is another way of talking about operators, eigenfunctions, and eigenvalues. Now, one of the other really useful parts about operator mechanics is it turns out there's a very easy shorthand way to express this. And you should be aware of, because even if you don't end up as a physical chemist, you're going to run into this next notation. It's called Dirac notation, more commonly known as Brocket notation, as we'll see later. But the general idea of Dirac notation is that my Hamiltonian should be applied to a wave function or an eigenfunction. So this is going to be represented by my psi in what's called a ket. So this notation is called a ket. And this is another way of expressing my wave function. So I apply my operator to my wave function. I get my energy back times the wave function. Operators are in hats. Functions are in kets. And then if I'm not either in a ket or with a hat, that means I'm a numerical value. And that leaves us with just our energy. So make sure to be very careful on your notation so you don't miss a hat or a ket. So one of the other useful things about this Dirac notation is it can also be used to describe probabilities. So if I'm looking at the probability of a system, so this would be the probability that something is located in all space, which for a normalized function should be 1, I'd represent by the integral of my wave, of the complex conjugate of my wave function over the relative variable. Okay, a little annoying to write out, and especially because I should acknowledge that the first part of my equation is a complex conjugate, and the second part is just my function. Well, I can represent that again in my Dirac notation. This gives us what's called our Brocket notation, because this first term is called the bra. So bra, ket, bracket. A little bit of a bastardization of the language, but it really is a good way to try and remember these systems. So while the ket represents the function itself, the bra represents the complex conjugate of the function. And if I pair a bra and a ket together, this means I'm taking the integral of the system. So, and it's worth noting that it is implied to take the integral over all space. So it's not just simply an integral, but again, an integral over all space, which can be dependent upon which notation you're working with. So as you may notice, this can start to become a little bit more of a convenient way than just writing out in full integral form. So you'll often find this is the shorthand notation of choice amongst most physical chemists. Now, one of the things I want to emphasize now that we've introduced normalization, if I have a normalized wave function, the bra of psi with the ket of psi should always equal 1. Because if I'm taking a wave function times its complex conjugate, integral over all space, well, the probability that happens should always be just 1. However, one of the things where Dirac notation really starts shining is when I'm combining non-identical wave functions. So I have one mathematical function times the complex conjugate of a different mathematical function, and then I integrate these over all space. And we're going to find that this form of equation turns out to be really useful. That said, the answers can sometimes be a little bit more complicated. So we're going to be exploring this use of Dirac notation next time as we dive a little bit more in depth on dealing with the operators we use in typical quantum mechanics. Until then, take care.